We are very, very happy to have Kamalika Chaudhuri today with us. Dr. Chaudhuri is an associate professor of computer science and engineering at UCSD, and she will be talking to us about a collection of work that she has led recently, and it's on reliable machine learning. There will be talk of robustness and adversarial examples, and overfitting in generative models, etc. So, Kamalika, welcome, and the floor is yours.
Thank you, Yanis and Nicholas, for inviting me. What we've been doing in my group for the last few years is we have been looking at various topics in kind of reliable machine learning. So what do I mean by this? You guys all know when you open a machine learning textbook, here is what you see, right? You have your training data, which is drawn IID from some data distributions. This is kind of the very basic statistical learning framework, right? And then this training data is fed into some algorithm, which comes up with a classifier. And then at the end, you have test data. So you build a classifier, and your classifier is evaluated on test data. Which is again IID samples that are drawn from the same distribution, right? And what makes your classifier good? Well, if you get high accuracy on your test data, that means that your classifier is good, right? And this is kind of the standard of textbook machine learning, and this is the framework where we work, right? The vast majority of machine learning research just works on this framework, right? Just looks at this framework. Reality, however, is much more complicated. So, whenever you try to deploy machine learning in practice, you realize that the picture is not quite as simple as that. So, for example, there are a whole bunch of issues that arise when you try to do machine learning in practice. So, things like robustness. You can't have a classifier which just does well on the test data. You want something a little bit more. You want it to be robust. Sample selection bias, your test data, it comes through some data gathering process. Maybe your data gathering process is biased in some way. Sometimes you're working with sensitive data, so there are privacy issues. So there's all kinds of issues that show up. And what we've been doing over the last, so what I'm interested in and what we have been doing over the last few years is look at some of these issues. And I'm kind of a theoretician by design, so by training and by design. So I am kind of interested in building the foundations of how to think about some of these issues, what kind of things work, what is a nice framework, and things like that. So this is kind of largely has been my group's work over the last few years. And what we will be talking about, what I'll be talking about today, are two kind of things that we have been looking at lately. So the first is robustness, and then the second issue that we will look at just briefly is overfitting. Okay. So, what is robustness? So, many of you, I'm sure most of you have seen these kinds of demos by now. They're quite popular. So, you have a neural network and you give it the image on I guess, the image on your left, and it's super confident that it's a panda. And then what you do is you add 0.007 times that little random noise that you see in the middle, right? The thing that looks like complete gibberish to you, and 0.007 times that. And now your neural network is even more confident that this is a given. So to a human, the images look more or less the same. I mean, I at least, I have glasses and so on, so I am old, but even I at least can't tell the difference between these two images. But the neural network is now completely convinced that this is a given, right? So what happens is you are doing small, somewhat strategic. So if you did this randomly, it would not make a difference. So what you're doing is you're doing a small strategic perturbation to inputs that are reasonably legitimate, right? Like, this is a natural panda image. And as a result, what happens is you get misclassification. And this can be quite serious. So for example, if this would happen on a street sign, so if you had an autonomous car and if this happened on a street sign, and then you could cause this car to think that a stop sign is an yield sign, and that could lead to a serious accident, for example, right? So this is this is something that needs to be addressed. And kind of here is what is known at this moment for these sort of problems. So these kinds of examples are called adversarial examples. The modified panda that the neural network thought was a given is it's what is called an adversarial example. So what is the state of what is known? So people have been studying this. Actually, there were some people who were studying it back in the mid 2000s, but then it died out for a long time. But people have been studying this since like 2013-ish, for example. And the state of the art is that there's a large number of attacks, and which are increasingly sophisticated, increasingly fast, faster, better, more sophisticated attacks. There are a few defenses, a handful of defenses, but we don't really quite understand as well what is going on with them, right? So why do we see these strange adversarial examples? Why are they happening? And one of the things that, as I mentioned, I'm basically, by training, I'm a theoretician. So one of the things that we have been looking at is that why do we have adversarial examples, right? So what is going on with them? Right? So if you look at classical learning theory, so there could be three, if you look at learning theory, there could be three possible explanations, right? So one possible explanation could be that your data distributions really overlap, right? So your pluses are, your cats look very close to dogs. So your data distributions really are very close together. And really there is no way to do any better, right? So you will always have adversarial examples. So that's, one possibility. Another possibility is that our we just have too few samples, right? So maybe our data distributions are far apart, but we don't really have enough samples that we could just kind of separate them robustly, right? So that's a possibility. And there's some limited evidence that some of that may be happening. And then the third possibility is that the training algorithms that we are using, they are somehow not built in for robustness, right? So these are kind of the three possibilities that could happen. And I will kind of give you the short answer as to what we have found. So what we have found is that the answer is really number three. So the answer is really that the algorithms that we are using are perhaps not the right ones. And so what we believe is that we need to be focusing on building the right examples, on building the right algorithms that are biased the right way. Okay. So this might be probably a good time. So now I'm going to launch into more details, and let me quickly check if there's a question. Okay, not yet. So then let me continue. And so that's kind of what we will be talking about for the robustness part of the talk today. Okay, so let's first start with some background. And you guys all know this. The kind of problem setup that we are looking at right now is classification. And we have these xi yi pairs. So the xi's are our feature vectors, yi's are discrete labels. And what we want to do is we want to find a prediction rule in a class to predict the y's from x's, right? So for example, it could be a linear classifier. That's kind of the very basic thing. It could be a neural network and so on. Okay. And again, standard machine learning, kind of textbook machine learning that we started out by talking about works in the statistical learning framework. What happens over there is that training and test data comes from some underlying distribution D. And what you want to do is you always want to find a classifier F that will maximize the accuracy. And the accuracy is the fraction of times F of X is equal to Y, right? And then the fraction or probability is according to this distribution D, right? And this is this is kind of the goal of the statistical learning framework. Okay, so how do we build robustness into this? To build robustness into this, what we do is we also look at our robustness measure. And what we have is we introduce two other things, right? So one is a distance metric D. Typically, to keep things simple, we take this D to be something simple, like either L infinity metric or L2 metric and so on. And the second thing that we are going to introduce is what is called a radius S. Okay. So we say that a classifier F is robust with radius S at a particular point if for all x prime which are within distance, within distance S of x, your classifier is predicting the same thing. So pictorially, if you look at that red point, you see a little ball around it. Your classifier is robust at that red point if it predicts the same thing in that little red ball, right? So, and if it is robust with radius S, then there are no adversarial examples within S of this example X. Okay, so this is how we kind of measure robustness. And, so what this is kind of trying to capture is the fact that we are looking at small perturbations, right? We could take an image of a panda and we could completely replace it by a given. Sure enough, the classifier is going to be wrong. What we are hoping to do is we are hoping to say that the classifier is correct if the perturbation is small enough, right? So this implies there's no adversarial examples around X. And the kind of metrics that we will look at as we go along are things like, adversarial accuracy, which is the accuracy against adversarial examples at radius S. And also we will, look at, of course, clean accuracy. So clean accuracy is the standard accuracy, right? So now we have kind of two metrics in space. Okay.
A quick question, if I may, on this definition of robustness. Is it exactly the same as demanding a strictly positive margin?
That is an excellent question. Yes. So basically what this comes down to is our margin. So let's say if your distance metric is L2, then this is an L2 margin of S. That's what it comes down to.
Okay.
Okay. If you change your distance metric, then your notion of margin would change. It would have to agree with this, with the distance. Yes.
Right. Thank you.
Okay. So, so what do we mean by robustness in neural networks? So what happens for robustness in neural networks? So let me give you a quick background. So this is kind of the way we will look at things. So if you remember, in a neural network, what is happening is we are looking to compute some function f of x, and f could be f is the probability values before, let's say, rounding. And here we will by the way, here we'll mostly be talking about binary classification, just to keep things simple. Everything extends to multi-class, but things just get a little bit more complicated, and I don't want to go into that for the purpose of the talk. So what is happening is that we have some function f of x, and the classifier will let's just say just round f. Right? So let's say if your f is positive, then your classifier will output plus. If your f is negative, then your classifier will output minus. And in this case, what we are looking for is we are looking for an f that is smooth or locally smooth, right? So if your f is locally smooth around your data points and your f of x is away from 0, then your f is robust at x, right? So this is the kind of thing that we are looking for neural networks. Okay. Okay, so again, what is known for robustness in neural networks? Again, there's a very large number of attacks. There are a few good defenses. However, the problem is all the defenses that we get show a robustness versus accuracy trade-off. And what do I mean by that? What I mean is that as the adversarial accuracy goes up, so we have a bunch of methods where, which have pretty reasonable adversarial accuracy. But as the adversarial accuracy goes up, what you see is that the actual accuracy, the clean accuracy, actually goes down, right? So the clean accuracy is this, especially for the slightly more complicated data sets, there is quite a gap between the clean accuracy that you could get out of natural training and the regular clean and the clean accuracy for the robust methods. And there's been some prior works which have claimed that this may be inevitable, right? And the question that we are going to ask ourselves is that, is this, Does it have to happen? Does there have to be a robustness accuracy trade-off? And what we are going to argue today is that the answer is no, especially if you are looking at, for example, real image data sets. Okay, so that's what we are going to talk about. That's kind of the main message of this talk. Okay, so what do real data sets look like? So before we get to real data sets, let me start out with a definition that we kind of came up with. This is a definition of R separation. So what does R separation mean? R separation means that your a data distribution is said to be R separated if, when you draw 2 points from this distribution, if these 2 points have different labels, then the distance between them is greater than equal to twice R, right? So what this means is so let's take a quick look at what this might mean, right? This doesn't mean that your data set is separable linearly or it's separable through some simple functions. What it does mean is that, your data set might be really complicated. The pluses and minuses, the reds and the grays might be all mixed together. However, the reds and the grays have to be distance 2R apart, right? And you can imagine there could be like really complicated decision boundaries, classes that are mixed together. The only thing is that the reds and the grays are distance 2R apart, right? And why is this R separation interesting? The reason why this R separation is interesting is that we can show something there. And what we can show is that if our data distribution is R separated, then there exists some function which is A, locally smooth. B, if you round it, you can get accuracy 1. So it can be perfect. It is locally smooth. It can be perfectly accurate, and it can have robustness radius R, right? So this S will be equal to R. So if you want your S to be equal to R, this robustness radius to be equal to R, you can get such a function which is perfectly accurate with robustness radius R and is locally smooth, right? So if your data distribution is R separated, then at least in principle, you can get both robustness and accuracy. There does not need to be a trade-off, okay? Now the question is, what happens for real data? And what we see is that real data is R separated. So this is so we looked at 4 standard image data sets that are heavily used in adversarial example experiments. There's MNIST, Cypher, 10, SVHN, and the last one is a restricted ImageNet. It's called restricted ImageNet. So it is a kind of a specialized, a subset of ImageNet that people use for these experiments. And what you have in the first column is the separation, right? So this is the minimum distance between 2 images which have different classes. And the separation, so this is basically 2R that we are talking about. And on the right column, what you have is a typical value of S. So these are typical values of adversarial, radii that people use for their experiments. And what you can see is that 2R is usually much larger than S. So if you double S, 2R, the separation is usually much larger than that, right? And so you can see the last 2 data sets, there are little stars. So what the stars mean is that SVHN, for example, is slightly noisy and it has 2 images that have the same label. So there are a few noisy data points. And restricted ImageNet is also like that. So there are 2 or 3 images that have the same label. But if you remove them, and we are talking about removing less than 5 images, right? So here we are talking about removing less than 5 images. So if you remove less than 5 images, then you get something like this. What you get is that your real data sets, or at least, the kind of benchmark data sets that we use, they are very much R separated, right? So they are very much R separated according to this measure. And for, especially compared with the the kind of adversarial example radii that are used in adversarial example.
We have a question.
Yes.
On the chat, Sharan has a question. You want to ask it, Sharan?
Go ahead.
Sure. So what is the distance metric and is it learned?
No. So here the distance metric is L infinity, which is very standard for adversarial example experiments.
Okay.
So you can do other distance metrics. People have done stuff with other, more perceptually aligned distance metrics. What they find, so what happens is that the attacks and the defenses, they all become more expensive in terms of running time.
And we have a second question by Reza in the chat. Reza?
Yeah. Can you give us an example of data set which is not R separated? Like real data set.
So, for example, a bunch of things that people use in, like credit risk prediction, that sort of stuff is not always R separated. No, not even those. So as far as I know, so things like, the things that people use in a lot of this kind of interpretability style experiments. So a lot of the social applications, those are not always R separated.
So generally, oh, sorry, go ahead, Reza.
No. I just want to say that I'm not familiar with those data sets. So, but yeah, so I believe it.
I think it would be any distribution whose class conditionals have overlapping support, right?
Exactly. Class conditionals have overlapping support.
We have more questions or comments in the chat. Adam?
Let me take a look. Let me take a look at the chat. So far, good news, right? R separation. Yes, that is true. So, but Adam is saying that it is good news. S is much less than 2R separation. Should a model should still do fine in theory, but they don't actually in practice. That is kind of the main message of the of the paper. Okay. So as Adam pointed out, that in principle they should be fine, but in practice there is a gap. Right. And we kind of try to understand why this gap is happening. And, this is kind of the big open questions in this field, right? To close this gap and, to close this gap between theory and practice.
Right.
Before
you proceed, I'm sorry for the interruptions. I think we have a couple more questions on this particular table. So let's take these two questions and then we'll move on. So Sharon.
Sharon is saying R separation is an original feature space. What about passing it through 10 neural network layers? So, we have some kind of preliminary experiments with that. If you pass it through the neural network layers and if you look at feature space, the R separation is actually is still there. It still happens. It's still there.
But that would mean you need to constrain the Lipschitz constant of the neural network in some way, else things can just become arbitrarily far apart, right?
Yes. So you do need to do that. There's some work by, I think, Roger Gross's group towards this. But then I think what happens is they also lose some expressivity. So again, it's I leave you with that open question. It's a big open question in deep learning is how to solve this. Okay. By the way, I think the questions are excellent. What that means is there's interest. This is wonderful. And Reyhane has a question. I feel this works better when a group pixel is changed, but how good is it for one pixel attack? So what you're asking is what you mean is what happens when one pixel gets changed, right? So that would be L0.
Yes.
So we haven't looked at L0 separability. That is an excellent question. We get similar results for L2, L1, and L infinity. We haven't looked at L0. That's an excellent question. The answer is I don't know, but that's excellent. Okay, so let me go ahead. This is wonderful. I'm very glad people are asking questions. Okay, so what accounts for this gap? And again, we don't have very definitive answers here, but we looked into this. We did an empirical study where we looked at those 4 standard image data sets. We looked at a bunch of models and then a few different training methods. And what we tried to do is we tried to measure the local smoothness, the accuracy, as well as the adversarial accuracy. And the first question that we kind of asked ourselves, so we were looking at this kind of smooth. So, we kind of started with this thing that if our neural network, the functions that we get are locally smooth, then we are getting more and more robust, we are getting robust solutions. So is that generally the case? And here is kind of a toy version of what we found, right? So I'm just showing you the results for CIFAR 10. MNIST turns out to be a very easy data set, so there everything works. So it's not like super duper interesting, but CIFAR 10 is kind of the typical, it's kind of the typical case. So which is why I'm showing it to you. And here what we have is we are also, so you know what accuracy and adversarial accuracy are. We are also measuring the Lipschitz constant. So high Lipschitz constant means things are less smooth. Right? Low Lipschitz constant, low good, high bad. And then we have the generalization gap, which is kind of the regular gap between training and test accuracy, and the adversarial generalization gap, which is the gap between adversarial, the adversarial accuracy around of the training points and the adversarial accuracy around the test points, right? So for the training points, you look at adversarial examples around them and see if they're correctly classified, and you do the same for the test point, and you look at the gap, right? And what we found is, so these are, a whole bunch of different methods. And what we found was we can mostly group the methods into two groups. The red, so I'm just going to call it the red group and the gray group. So the red group is those where the classifiers are less smooth in the sense that the Lipschitz constants are somewhat higher, but they are overall a bit more accurate. Okay, so they're less smooth, more accurate. And then the second group is those which are more smooth, but not as accurate. So what you see over here is, so this GR is gradient regularization. ZR is kind of noisy. Sometimes it behaves better, sometimes it doesn't behave as well. So maybe let's ignore GR for now. But overall, what you see is in the red group, what happens is the natural accuracy is kind of high. The natural the clean accuracy is kind of high. The clean generalization gap tends to be low. However, the adversarial accuracy is really low. And the Lipschitz constants are also high, which means these classifiers are not super smooth. Whereas in the gray group, what you find is that the natural accuracy is quite a bit lower, right? So you can see these are in their 80s, whereas, so let's, maybe let's ignore GR, whereas for natural and LLR, the natural accuracy is in the 90s. Adversarial accuracy is much higher. You can see it's in the 40s to, like 42 to 47, whereas in the red group, the adversarial accuracy would have been, 0 to 20s, right? And the Lipschitz constants are also lower, which means these classifiers are more smooth and less accurate, right? And so as you see, the generalization gap for this gray group is actually also quite high, right? Because you can train everything to perfection or close to perfection, whereas while testing, things are a lot worse. Okay, so it seems like at least for the more robust solutions that we have, so these are kind of the state-of-the-art robust solutions, right? So the more robust solutions that we have, what happens is the generalization gaps tend to be a fair bit large. So, so the generalization gaps there are lower on an average of the red group and, higher on an average for the gray group. So our thesis is what we should focus on is the generalization. And we tried a few things. So we looked at, in particular, we looked at dropout. And what we found was that dropout did help. A little bit, not a lot, not to the extent that we would have hoped, but it did help a little bit. So here what you are seeing is we are looking at natural. So I removed GR and LLR because they got really hard to train with dropout. So you're looking at natural. And then we have these gray methods, RST, adversarial training and traits. And what you are looking at is, so the first row is what you have with dropout. And the figures within parentheses is what you had before, right? And I have colored things, the text is colored red if there was a reduction. So what you see is that overall, or there was a reduction as in there was an improvement, right? Not necessarily reduction, there was an improvement. right? So what you see is for natural, it doesn't matter as much, but overall there is at least a little bit of an improvement. So one is that in the accuracies and the adversarial accuracies, there is a little bit of an improvement. The generalization gaps also there is a bit of improvement. And in the Lipschitz constants, mostly there is, especially for, this method called trades, which tries to impose local Lipschitzness directly. In the Lipschitz constants also, there is a bit of an improvement. So what we see is, again, the effects are not huge, but what we see is that dropout does reduce the generalization gap a little. So overall, our observation is that the smoother methods tend to be more robust. The methods that are locally smooth, that have low Lipschitz constants, they tend to be more robust. The less smooth methods tend to be less robust. The smoother methods tend to have a larger generalization gap. And also dropout does help a little bit. I mean, it doesn't help completely, but it does help a little bit in the sense that it does reduce the generalization gap a little. Okay? So in conclusion, what we find is that for neural networks, real data is R separated. So robust and accurate neural networks should exist, right? However, our current algorithms do not find them. And this is plausibly because they don't generalize well enough. And so what we need to do is we really need to focus on better methods for adversarial generalization. Okay, so maybe this is a good time to take a few questions.
Yeah, we can. There was a question by Robin, which I kind of answered, but I'm not sure if I completely did in the chat by mentioning something that you said earlier. Robin, would you like to ask your question again?
Yeah, I was just thinking of like realistic data sets that have like noise in the labels. So like some amount of the labels are incorrect, and then would that mean that our separation is not there, and then this wouldn't hold? I guess if you could comment on that situation, because I think that's a very common scenario. And I think the case of having only 5 data points you could remove to restore R separation, I think maybe, but I think in most realistic data sets, the sizable data sets, I think that seems unlikely to me.
Right. Well, for at least for the standard data sets we looked at, this was definitely the case, that there were just, less than 5, right? SVHN had less than 5, restricted ImageNet had less than, 5.
Don't you think these data sets are uncharacteristically hygienic compared to if you had a bunch of labeled data from hospitals or something? You'd get a lot of bad labels and mixed in there and stuff like that. That's it's not a.
Yeah. That is definitely, I agree with you. That is possibly true. So that's possibly true, but there's a couple of things here. So one is that, which I won't go into today, but we do have an algorithm for making data sets R separated, removing the minimum and making it R separated. We call it adversarial pruning. And it seems to help not for neural networks, but it seems to help for other things like, nearest neighbors and, this kind of stuff. So there are things you could do if you really cared about robustness for those kinds of for data sets. This is something you could do. You would sacrifice a bit of the accuracy, but you could do this sort of pre-processing.
Cool, thank you. That's awesome. Thank you.
And maybe I think it was Sharon's point earlier. Maybe if you were to look deeper into learned metrics, essentially, or learned representations.
Yes. So
maybe that can help.
Yeah. So I think in the learned representations, the classes are usually, even better separated. They're better separated in feature space than in pixel space. But what that means is that the learned representations themselves are not smooth with respect to the pixel space.
Okay. I have one more question.
Mm-hmm.
There's this recent work that I'm just superficially familiar with.
Mm-hmm.
There's a recent paper discussing a trade-off between robustness and accuracy. And it's a paper from, I guess, John Ducci, Percy, Liang is a co-author, I think. It's Stanford paper. I think it's a very recent paper. I don't know if it's from this summer. And they discussed the trade-off
Right. So that is actually, they introduced this algorithm RST. So that is this baseline RST. So what they do is, I didn't quite go into what are the algorithms that are used. So the standard algorithm would be something called adversarial training, where what you would do is you would minimize your training loss on the adversarial examples, right? And what RST does is it minimizes lambda times the adversarial loss plus 1 minus lambda times the clean accuracy. And it does help. So it does help by a few percent points, especially if you tune the parameters well. But it doesn't help, but it doesn't completely address the problem. I mean, you still have this generalization issue is much more fundamental than that.
So would you say that this kind of method, you mentioned that for these R separable data sets, it should be possible to get, like have your cake and eat it too, right?
Exactly.
So would a method like RST be able to do that under those assumptions of R separation?
They are currently not able to. And the reason why I think is, so there's what we think is what is going on is the problem is a little bit deeper. And so I guess, when we had these neural network that produce these really good results on natural images, that came through years of work, right? Like there was a lot of work in getting the right architecture. There was a lot of work in coming up with a lot of these right optimization algorithms. And I feel like with robustness, we may have to redo some of that stuff again, right? So maybe there are different architectures that work. Maybe there are different optimization algorithms that work. And the issue here is, and as you know, in deep learning, architectures and optimization algorithms are intimately tied with generalization, right? It's not as simple as linear classification where you can separate the two, right? So our thesis is that some of that stuff is going on. The generalization is really the problem, and the solution might come from better architectures or better optimization algorithms. And it's not just the loss function. So far what has happened is that the community has been focused on different loss functions, and we think that it's not just the loss functions.
Okay, that's exciting then. That's an interesting, exciting thesis to push for changes in models. There was one last question here before we move on. Reyhane, you want to ask a question?
Yeah. So is there any difference that you notice if you use a natural and a synthetic image in terms of accuracy?
So I think in general, what is quite well established is that if you have synthetic images, right? Like if you have neural networks, the reason why they work so well is they have some sort of inductive bias, which is very tuned to natural images or natural audio, right? So if you have like random images, then these neural network architectures are not going to work very well.
Okay, yeah.
So the results will be, it'll be quite unnatural.
And Sharan had the last question.
Sorry, I don't understand why we are being optimistic, because isn't it? I mean, suppose we become robust to like one class of perturbations, I can always design like another class of perturbations which will basically screw the classifier up, right? So maybe in the end, the thing that matters is that the network should be robust to perturbations that we ourselves are, like humans, are robust to. And because it's like just a meta no free lunch theorem, no?
Right. But, the thing is that that's absolutely true. But, right now they're very far from that, right? Like if you look at that panda and the gibbon, right, the images, nobody in their right mind would think that it's a panda. I guess what I'm saying is that right now we can't even be robust to things that are off by like very, very little. It's so little that the metric doesn't, almost doesn't even matter.
But very little in what distance metric? So
it doesn't matter, you know, like L infinity, if 2 pixels change and then you are suddenly non-robust, right? Like that's where we are right now.
yeah, okay, I agree that things are especially bad now, but yeah,
No,
okay,
I mean,
that's
I
fair.
mean, what I'm trying to say is that what metric will become a more important question when we can get robustness to very small perturbations, right? And then it will be like, oh, do we? Because then the L infinity and the L2, these results will start differing. Right now, you know, we are kind of at the point where if you change a few pixels, things just go completely haywire.
Okay, yeah, that's fair. Thanks.
So I guess, yeah, I mean, I agree with you. I mean, you know, but we are quite far off from the ideal at this point. So,
All right. I think we're done with questions for this section, Kamalika, so
okay.
you can
So let me
proceed.
skip over. I wanted to talk a little bit about non-parametric, but let me skip over to the second part of the talk so that I can get to, or you know what, let's, okay, how about this? I'll take a poll. One thing I could do is I could talk a little bit about non-parametric methods and robustness, and then the other is I can talk a little bit about overfitting. What would people like to hear? So I don't think there's time for both. So
Okay, people can voice their opinion on the chat.
yes,
Non-parametric models and adversarial examples or overfitting.
non-parametric. Okay, I see one non-parametric.
Okay.
Non-parametric. Okay, so looks like non-parametric is winning, guys. Okay, good. This is a little bit more theoretical, but let me then go ahead with non-parametric.
Okay.
So this is, sorry, just give me a second. Okay. So we were again, talking about robustness. So, with neural networks, what we found is that in principle, there shouldn't be a robustness accuracy trade-off. But in practice, there is. And what we think is to blame is the algorithm. Okay. And, remember, next what we will do is we'll look a little bit at, some of these non-parametric methods like, nearest neighbor decision trees. And, as I said, I'm a theoretician. So, I also work on these kinds of things. And remember, we were trying to understand why we have adversarial examples. So, one possibility was that our data distributions overlap. The second possibility was that there might be too few samples. And the third possibility was that we may have a bad algorithm. Okay. So now, we are going to look a little bit at non-parametric methods just to, I'm sure you guys have seen all of this before in your machine learning 101 classes, but just to remind you, what are the kind of things we are talking about are, things like k nearest neighbors, right? Where, you have a test point, you look at its k nearest neighbors according to some metric and you output the majority label. Then there are things like decision trees where, you build something like a little tree, based on this, and then, you just follow the tree down, then you get a test example. There are other, things like this, like random forests, kernel classifiers, and so on. They all fall into this umbrella of what are called non-parametric methods. Okay. So what do we know about non-parametric methods? So there's a classic, so before I get to this, let me quickly define the Bayes optimal classifier. So you guys have probably mostly seen this. So this is a classifier. Remember, we were talking about accuracy in the beginning, right? Like we were looking at, we wanted to maximize accuracy on the data distribution, right? The Bayes optimal classifier is the classifier which has the highest accuracy on the current data distribution. And, again, this is a distribution quantity. So it's not something that you can find with a finite number of samples. But so it's only reachable in the infinite sample limit. So once your n goes to infinity, you will have, you could aspire to get to the Bayes optimal classifier. And, in real life, what you can hope is that as your n grows, you will slowly come closer and closer to the Bayes optimal, right? And what is known about non-parametric methods? So this is, a classical theorem in statistical, I think in statistical theory. And, this was even before I was born. So this was proved by Stone in 1977, even before I was born, which is that as your training data size grows, the accuracy of a lot of these non-parametric methods. So there are a few kind of details, but basically if you set the parameters right, then the accuracy of a lot of these non-parametric methods, like nearest neighbors, decision trees, if you do things right, will converge to the accuracy of the Bayes optimal classifier. So if you have a lot of data, then in the limit at least, we will be kind of doing the right thing. Okay, so this is kind of something general that is known. And the question is, what can we say about robustness? So first of all, when we were talking about accurate classification, what we were talking about was the Bayes optimal, right? However, if you have, we just talked about these R-separated distributions, you have your pluses and minuses are separated. Your Bayes optimal is actually undefined outside the support of the distribution, right? So, for example, if you have a red region and a gray region, any of these blue lines could be the Bayes optimal. In fact, anything in between, right? Anything that separates the reds from the grays would be the Bayes optimal. But if you look closely, not all of them are robust, right? So, what would be the limit? So what we do is we propose a limit and we call it the R optimal. So in our paper, which is actually going to appear in AI Stats, we propose this limit and we call it the R optimal. And it is the classifier that maximizes, anyway, I won't go into the details, but what we call astuteness, which is, kind of accuracy when it's robust, right? And what this classifier does is, again, this is a limit object, so you know everything, right? So what this limit object does is, if you are within distance R of the support of the pluses, then you're going to predict plus. Otherwise, you're going to predict minus, right? So this is your R optimal classifier. Okay. And this is defined for, so the current definition that I'm showing you is defined for R separated data, but we can also define it in other cases when the supports overlap. I mean, I don't want to go into the details for the purpose of this talk, but when the supports overlap, you can also define it, but things get more complicated. Okay, so this is your R optimal. This is the limit or robust classification. And what we can do is we can actually show, this theorem, that Stone's theorem from 1977 that we talked about. What we can do is we can show robustness analogs of Stone's theorem. So we can provide various conditions. So these are fairly technical conditions under which your non-parametrics will converge to the R optimal classifier in the large sample limit. And the interesting thing here, so the conditions are, fairly technical, I mean, I'm not showing it to you just for for time reasons. But the interesting thing is what does converge. And so what we find is that, nearest neighbors, so especially for R separated data, nearest neighbors converge to the R optimal in the large sample limit. Kernel classifiers converge to the large sample, to the R optimal in the large sample limit. But the interesting thing is that there are classifiers which will converge to the Bayes optimal, but not R optimal. An example of this is something called the histogram classifier, right? That would converge, so as n goes to infinity, that would converge to A Bayes optimal, not necessarily the R optimal. Another interesting classifier that people use quite a bit is decision trees. That would, or certain kinds of decision trees. Stone's theorem doesn't cover all kinds of decision trees, but it covers certain kinds. That would converge to the Bayes optimal, and which follows from Stone's theorem, but not the R optimal. And I will leave you with a picture about, kind of what goes wrong. So what happens with decision trees intuitively is what you see in this example, right? Here, what is happening is you have these two, you have the reds and the grays, and they are separated, right? Because they are kind of tilted, right? But they are 2R apart. And if you are building a decision tree, what you would do is, like if you take any standard decision tree method, in fact, any decision tree algorithm that I know about, what it will do is it will choose a threshold in between, and it will have this 2-node decision tree. It would choose this, kind of blue threshold in between, and it will say, okay, to my right, I will just predict gray. To my left, I will just predict red, and I am done, right? And that's it. You just stop constructing the decision tree. And this will be a perfectly accurate solution because there is nothing in between, but it won't be robust, right? And this is kind of the problem with decision trees. Okay. So in conclusion, what we find is that also for non-parametrics, what has happened is that the robustness depends very much on the training algorithm, right? So if you are, if your algorithm is, it depends on what you are doing basically. So if your algorithm is basically nearest neighbors or kernel classifiers or something like that, then you will be robust. As you get more and more samples, at least in the limit, you will be robust. However, for things like decision trees, where you are kind of splitting the space up into cells and then you're stopping when you're accurate, what would happen is that you will not be robust in the large sample limit. For those kinds of cases, you will, even if your data is well separated, you would converge to the Bayes optimal, which is fine, but not to an R optimal. Okay. So in conclusion, we looked at this, we looked at what the limit should be, right? When you're looking at robust classification, what should be the large sample limit? What is analogous to the Bayes optimal? And we proposed this R optimal. We showed that nearest neighbors and kernels will converge to R optimal for this kind of R separated data, but not things like decision trees, right? And so what we find, if we go back to this picture, what we find that even for non-parametrics, the robustness will also depend on the training algorithm. And this sort of makes sense because mostly so far we have mostly been focused on accuracy, right? Like all the things that we have done, machine learning, mostly we have been focused on getting more and more accurate classifiers, and mostly we have not really thought about robustness. So it's not a great surprise, but I think for robustness, what we really need to do is we really need to focus on building the right algorithm. So, and with this, I'll maybe stop and take some questions.
Oh, all right. There was some interesting discussion about the connection between R separation and maximum margin, the idea of maximum margin classification, right?
I see. Excellent question. Excellent question. So, yes. Yes. So for max margin in support vector machines, so R separation is kind of different in the sense that it doesn't need to be, the data doesn't need to be linearly separated. It is you are absolutely right. It is very closely related to maximum margin. In fact, if your data was linearly separated, and let's say you care about L2, then, SVM would give you the right solution, right? So if your data was, okay, it wouldn't quite give you the R optimal. Maybe right. I should always have a picture.
So I think that I misspoke. Essentially, the comparison is between R optimality and the max margin property, because R separation is a property of the data. Now we're discussing about methods, right? So some methods give you maximum margin. Decision surfaces in general, they don't have to be linear, and R optimality seems to have some connection to that, but it's not exactly clear.
So R optimality also depends on the metric. So I think what Nicola is saying, max margin can be defined on non-linearly separable data with the use of a kernel. That is absolutely true. But what you want is margin in the pixel space or margin in the original feature space. So for non-linearly separable data, so your kernel has to be such that it gives you margin in the in the original feature space, in the original X space. I think that's kind of the difference. That you're absolutely right. I mean, there are some nice connections here that we haven't fully explored. So there are some connections. So in some sense, you can think about R optimality is some sort of margin of R. It's some form of non-linear margin of R in the pixel space. Maybe that's kind of the right way to think about it.
Mm-hmm. Okay. So let me see if I can take one question. So we have a little bit more time. a lot. But if you want, we have more time for you to go to the second part of your talk.
The second part. Okay, so maybe I'll try to. Oh, I see. Renan has a question. Example can be stated for R optimal where max margin fails. Well, depends on max margin on what, right? So here, for example, if your data is not linearly separated, then your max, right? Then you can still have an R optimal, right? If your data is not linearly separated, so examples, kind of complicated examples like this, you can have a curve which stays distance R from each of the supports, right? So that would be a max margin solution. But if you do SVM or like linear max margin, you won't get to it. I think the kernel thing is a very interesting question. We haven't looked at it super duper closely, but what it means, but then one thing with kernels is that the kernel has to also respect distances. So I guess my answer is, if the kernel respects distances in the original feature space, then I think those solutions can give you max margin. Otherwise, probably not. But again, this is not a well thought out answer. This is like an educated guess.
Okay. Okay.
And I think there are interesting things to look at there for sure.
So were there any other questions that might be about something else other than the connection to max margin?
I have one, but I don't want to get us off track. It's quite general. Like, how do you think about the connection between adversarial robustness and robustness to like distribution shift, and how do you think about the role of causality in robustness, as opposed to these types of models are more associative model, ML. So how do we make sure that we're not falling for some associative features?
We are definitely falling for associative features. So, I think if we could get good causal models, then robustness shouldn't be a big problem. Again, this is just intuition. It's not something I can prove. However, I think robustness, if you only care about robustness, then the problem is a little bit more simpler than that, I think, because the problem is essentially, close to kind of a nonlinear large margin problem. It's not really, causal inference is, I think, trying to solve a harder problem. And I feel like if we could solve the harder problem, my conjecture is that robustness wouldn't be an issue.
Thank you.
Thank you. Okay, so now, Kamalika, we have maybe about 12, 14 minutes or something like that net time, because there will be some questions too. Is that, so I can help you make a...
I can, what I'll do is maybe I can just kind of give the overall brief idea, if that's okay, and then not go too deep into the experiments. Okay. So the next part of my talk is about something just kind of, related, but somewhat related, but mostly quite different, right? So here what is happening is that, we are kind of looking at deep generative models. And, deep generative models have been highly successful. They can produce very realistic images. They're also being used for other sort of stuff. So, for example, people are using GANs to produce synthetic data in cases where privacy is a concern, synthetic patient data, for example. So they are, they've been highly successful at this point, right? But people have also started thinking about whether they overfit, right? And, as you know, I'm kind of a theoretician. I have a somewhat, I have a somewhat theoretical perspective on things. And one of the things that we've been trying to understand is, what does overfitting actually mean over here? So what is an example of overfitting? So we are in fact concerned with a specific type of overfitting. Let's say you have a generative model which just completely reproduces its training data, right? And this can, for example, have some privacy concerns. So if you're using a generative model like this to say, oh, I am generating synthetic patient data because I have privacy concerns about releasing the real patient's data, well, you're just releasing the real patient's data at this point, right? So so that could be a privacy concern, right? So and also, I mean, obviously there's a privacy concern, but we would also like our generative models to come up with just, things that are new, right? Things that are kind of like like the things that were in training data, but we wouldn't really like it to reproduce the training data. I mean, there are simpler ways of doing that takes less energy, which is just copy paste, right? So that's the kind of thing that we are looking at. Okay. So what is the setting over here, and what is the classical view of overfitting? Well, the setting is that, you have some training data that goes into some algorithm which produces a generative model. You use your generative model to draw some samples, and then you evaluate how good this generated data is. And sometimes you can have qualitative metrics, but in a lot of times what would happen is you would have an independent test sample, and you can use this independent test sample, the generated data and the training data to come up with some sort of evaluation score. Okay. And classically, what would happen is what we would see is something like the following. Here, what we have is on the x-axis, what we have is model complexity. And on the y-axis, what we have is likelihood, right? And the red line represents the training likelihood. So usually what you're trying to do is you're trying to maximize the likelihood. And as you keep making your model more and more complex, what happens is that your training likelihood keeps going up, whereas your test likelihood, the likelihood of the test data given model, it will go up, and at some point it keeps going down, and that's kind of when you are overfitting, right? And this is kind of, this is the standard classical way of looking at stuff, right? So when the probability of the training data given model becomes much higher than the probability of test data given model, then that's when you are overfitting. So this kind of, I mean, this is a good way to detect overfitting. However, this might have some problems. So one of the problems would be that for a lot of models like the VAEs, the likelihood itself is kind of intractable. So you can get lower bounds, but you can't exactly get, you can't always get the exact likelihood. And, if things are sensitive, then it might throw you off. And then for things like GANs, you don't really even have a likelihood. You only have samples of this model. Right? And a lot of these models will have tens to hundreds of millions of parameters. So overfitting may be a serious concern here, right? So kind of our main contribution in this paper is to define a formal notion of overfitting, and then we use that to get to a test. Okay. So what our main contribution is to formally show, or rather formally define, and it's, let's just say it's a kind of an observation, is that there are two distinct formal notions of overfitting. Okay, and that we are going to call them overrepresentation and data copying. Okay, so what is overrepresentation? Suppose you have training data, some generated data, and a test data. You get an overrepresentation in a region C if the proportion of generated data in that region is much higher than what you would expect from the training set, right? Or what you would expect from the test set, right? So for example, if you look at this kind of toy example over here, in the top panel, you get a lot of generated points, but not as many training or test points, right? And so in some sense, if you guys are familiar with some of this terminology, this is like the opposite of mode dropping, right? So it's like overrepresenting a particular mode, right? So this is overrepresentation. In contrast, data copying happens when the following happens. So for data copying, we need a distance metric D. And again, things again depend on how you choose your distance metric. And we say that we are data copying in a region C of the space if, let's say, you drew your, you have your training samples, you have your generated samples and your test samples. If your generated samples are much closer to your training samples than an independent test sample that is drawn from the same distribution, right? So what this means is your generated samples, an example where that would happen is if you are copying out your training data, right? So your generated samples lie either directly on top of your training points or slightly away from your training points, whereas if you drew an independent test sample, well, those would look quite a bit different, right? So that is what we call data copying. And just to emphasize, overrepresentation is actually quite different from data copying. You could have overrepresentation without data copying and vice versa. So for example, if you had a mixture of 2 or 3 Gaussians and you equal mixing weights and you picked out 2 of them very accurately and you gave them 50-50, that is actually overrepresentation. On the other hand, if you just copied out your training points and just added a tiny bit of perturbation to them, there's really no overrepresentation if you're looking at kind of big enough regions of space, but there is data copying, right? Because you're very, very close to your training points. Okay.
Question?
Yes, go ahead.
Quick question. Doesn't the distinction between the two also depend on a almost arbitrary notion of neighborhood in some sense?
Definitely depends on the neighborhood, and choosing the neighborhood is actually quite important. So and in fact, it's important in generally generative models as well, because different generative models can show different behavior depending on the scale that you are looking at. So globally they may be okay, but locally they may be not. And this happens, in any kind of complex generative model, this happens.
And just to follow up, can I say that an example of data copying is actually overrepresentation if I zoom in?
If you zoom into individual data points, yes. Generally, what you would like to do is you would like to look at regions where you have, so the kind of regions you would like to look at is where you have a certain number of samples, like, I would say something like 50 samples, enough that you could do some sort of hypothesis testing.
Okay.
I mean, otherwise you can't say anything based on the samples. I mean, otherwise you don't even have enough data to say anything about what is going on at all.
Okay.
Right? I mean, you need to have like a few training and a few samples from the distribution, enough so that you can tell what is going on in this region. Otherwise, you don't have any data to say anything.
Okay, I have some follow up, but I will save it for the end of your talk.
Okay.
Thank you.
So there's a lot of existing hypothesis tests for overfitting in generative models. And, I mean, these are just 5. I mean, these are the 5 that we sort of compare with in our paper, but there's a lot more. And the surprising thing to us was, so when we started reading some of this work, the surprising thing to us was almost, I mean, with one maybe small example which detects limited forms of data copy, everybody tests for overrepresentation. Each and every one of those tests for overrepresentation, and most of them would fail to detect even exact data copying. Even if you are copying out your training samples, they would fail to detect it, right? And so so that was kind of a surprise for us. So when we looked deeply into this test, this is exactly what we found. And so what we are hoping to do over here is to find a test for data copying. Okay, so what would be the first thing you would think about doing for data copying? So what you would think about doing is, I mean, data copying, the way you define data copying is to find if your generated points are closer to the training data than an independent test sample. So the simplest test is you get a bunch of training data, get a bunch of generated samples, get a bunch of test samples. You check if the average distance between test samples and the closest training point, if it's higher or lower than the average distance between the generated samples and the closest training point, and if this is significantly higher, this difference, if it's significantly higher than 0, right? So that would be a hypothesis test. You can draw, you can draw various significance curves. And, if this is significantly higher than 0, you can say, yeah, we are data copying, right? The problem with this is that this suffers if your data has some outliers, which might happen in generative models, also in, usually any kind of data set. Then this test would have really high variance, right? Because one of the distances could be really quite high, and that could mess up your entire test, okay? Because you're looking at averages. So the simple solution to that is to use something called comparisons. So what you do is you look at distances between the test data and the closest training point, and distances between the generated data and the closest training point. So you look at all these distances and you check to see whether these distances are you look at comparisons, right? So you check to see, you do all pairs of comparisons, and you check to see on an average, are these comparisons, are these distances smaller or bigger, right? And if you stare at it a little bit, what you realize is that this test is exactly, this very classical statistical test called the Mann-Whitney test, right? Mann-Whitney kind of comparison test, where you are trying to, where you have, numbers from, two lists of numbers, right? Numbers from two distributions. And what you're trying to do is compare whether one distribution gives you higher numbers than the other, right? And this is exactly this Mann-Whitney test. And the Mann-Whitney test is actually very good because, it's really statistically, it's very efficient, and, a lot of things are known about it. So you can just do the Mann-Whitney test based on the distances. Okay. What could go wrong here? The thing that would go wrong here is that if you try to do a global test like this, the global test will fail for any kind of complex generative model, because these complex generative models, they're very heterogeneous, right? There are some regions where, there's a lot of data copying. There are some regions where things are not fit well at all. So there's, a fair bit of underfitting. The distances are very large. And when you put everything from these regions together, what is going to happen is that the test might work out fine, but you still might be data copying, right? And in fact, this is the problem. We can come up with examples that show that, this will be, right? This is a general problem, right? I mean, that is why these deep generative models are so hard to understand or test against, because they are very heterogeneous, right? And so what we did was, we came up with this algorithmic tool. So, I worked on non-parametric methods before, and this is kind of an idea that comes from non-parametric statistics, which is essentially what you do is you divide your space, your instance space, into cells, and then, and then you look at each cell. I mean, this is kind of what decision trees also do, and nearest neighbors, this is what implicitly that they're doing. So you can use a similar idea conceptually. So what you could do is you could divide your space into cells. The way we do it for our experiments is through clustering. Then you can do your test in each cell, and then you can put the test results together, right? So we can report weighted average of these one-sided test results. If the average looks too high, then you can go back and look inside each cell, right? And we do see that different cells are turn out to be quite different. Okay, so that is essentially our test. Okay, so how well does it detect data copying? Maybe I will go a little bit faster over this. So one case study we looked at was with VAEs. We looked at VAEs on MNIST. And the reason why we chose this is because VAEs are known to, especially if the latent dimension is very high, VAEs are known to overfit. I mean, they are known to spit out examples which are exactly the same as the training set, right? They are known to overfit. And the metric that we chose is, is a 64-dimensional latent space of an autoencoder from this Zhang et al. Okay, and here is kind of the results. So in terms of baseline, so the blue line is CT is basically our test. I guess CT is basically our test. And what you see here essentially is, so if you remember, I mentioned that there is one test that can detect some form of data copying, which is this nearest neighbor test due to Lopez Pass and OQUAB. We also looked at generalization gap. And what we overall found is that as the latent dimension goes up, you are doing more data copying, and our test score does seem to go up. Whereas generalization gap doesn't always go up. I mean, generalization gap, you can get some signals, but for VAE, you don't exactly have the log likelihood. You have the elbow. You don't always have all the signals. And this nearest neighbor test also does okay. It does keep going up, but you don't have like a concrete threshold. So the nearest neighbor test, it's called the nearest neighbor test. The theory predicts that half is where data copying happens. But here you do see some going up, but it's not exactly at half. So it doesn't really happen where the theory predicts, right? So you can't really say, oh, this is more than half. So, so things are bad. Okay. And then we also looked at Big GAN, and we chose, so we don't really have the resources to train Big GAN. So we picked the Big GAN model. And then we chose 3 classes, which I think 2 of these are default classes for demoing Big GAN. And the third is like a random class, which has an object in the foreground. And Big GAN also has some measure of the sample quality. There's something called the truncation threshold. And we try to see what happens as we vary the truncation threshold. And I guess as the truncation threshold goes up, there is supposed to be more data copying. And as the truncation threshold is down, there's supposed to be less data copying. Here we don't have generalization gap because there's just the samples. And what we saw is that the nearest neighbor test seems to be more or less constant. You don't really see a trend. And these are, this is the test with 3 different parameters. And whereas our test does seem to go up, right? It does seem to go up as you increase the truncation threshold. So you are going towards more overfitting. It does seem to go up a bit. And we also looked at some of the images that we got. So one of the problems we had with Big GAN is because this is ImageNet, we only had 50 test examples per class. And we did some clustering. So the clustering that we could do is we could divide it into, I guess, 2 or 3 clusters. We couldn't do any more than that because otherwise each cell will not have enough points. And if the cell has too little points, then our test is not statistically significant. If it has too little test points, then it's not statistically significant. Overall, so the results are not, like if you look at it visually, the results are not super good because we don't have enough test samples to do a reliable test. But overall, what we found was if you had a cell which our test predicts that this is data copying, then the diversity of generated samples tends to be much less than a cell which is not data copied, right? So for example, if you look at the data copied cell, you see these are basically variations of the same coffee cup. Whereas if you have a cell that is not data copied, then what you see is that, they look like different coffee cups, different types of coffee cups, right? So overall, this is kind of what we found. And so finally, if you ask me, I think our most interesting contribution was formalizing the 2 notions of data copying. And then we presented a new 3-sample test for data copying. Okay? And so finally, what I will do is I will kind of leave you with some of these references. And these are kind of my co-authors who did most of the work. And I'll stop over here.